Okay, refrigerator is a cycle that transfer heat from low temperature to high temperature. So that means we have two thermal energy reservoirs. One is at low temperature, maintained at TL, and the other one is at high temperature, maintained at TH. And the rate of heat transfer is in this direction, from low temperature at the rate of Q dot L to high temperature at the rate of Q dot H. However, this heat transfer direction is against the second law of thermodynamics, so it doesn't occur, naturally. So we need to provide power, W dot net. So this is a refrigeration cycle. So the low temperature is going to be refrigerated space, and high temperature is going to be outside. So for example, if it is a refrigerator in the kitchen, so that's going to be the air in the kitchen. What about heat pump? Heat pump runs in the same cycle. However, we use different application. So this one also has two thermal energy reservoirs. One is at low temperature, T of L, and the other one is at high temperature, T of H. And the heat transfer direction is from low temperature. So we observe heat from low temperature at the rate of Q dot L and reject that heat to high temperature and at the rate of Q dot H. However, this is against the second law of thermodynamics, so it doesn't occur naturally. So we need to provide power. And in this case, this low temperature thermal energy reservoir is going to be outdoor, and the high temperature thermal energy reservoir is going to be indoor. So we heat indoor by observing heat from outdoor. In other words, by cooling outdoor, we heat indoor. Then how can we analyze their performances? We can use coefficient of performance, COP. So there are two COPs. One is for the refrigeration cycle. The other one is for a heat pump cycle. And how do we determine them? By the same rule that we used to determine the efficiency, desired output over required input. Then, what is the desired output, for this refrigeration cycle? Why do you have a refrigerator in your house? To heat the kitchen air or to waste your electricity? No, we want to cool the refrigerated space. So this is our desired output. We want to observe heat from, our meat, our vegetable, so we can let them fresh, right? So the desired output is going to be Q dot L. Then to run a refrigeration cycle, what we need to provide? Kitchen air? No, we need to provide electricity. So W dot net is the required input. On the other hand, for this heat pump cycle, what is the desired, output? Do we want to cool outside? Do we want to waste electricity? No, we want to heat the indoor. So Q dot H is the desired output. And what is the required input? We need to pay the bill, W dot net. By the way, the energy balance equation for both the system, we have the same equation, W dot net is going to be the difference in heat transfers. So Q dot H minus Q dot L. So we can rewrite this equation also in this way, Q dot L over Q dot H minus Q dot L. Q dot H over Q dot H minus Q dot L. So that's also how we determine coefficient of performances. Some books, like our textbook, we use beta for COP of refrigerator. We use gamma for COP of heat pump or COP. They use different words. So that's everything about how to evaluate the performance of refrigerator and heat pump. Any question? Okay, I know that it's too easy, right? So let's solve a problem together. Chapter 5 is super easy. I totally understand that, but don't worry about that. In chapter 6, our Mountain Everest is coming. Entropy, the hardest chapter in this course. But don't worry about that. Entropy won't be in your second exam. It will be in your final exam. To make the final exam, the most, like an ultimate boss. No, the final exam is too hard. So I won't make it comprehensive. No, that's not it. The final exam, it has entropy. However, that's the only theory, the chapter in, in the final exam. The chapter 8 and chapter 9, they are applications which are easier than, the theory chapters. So chapter 6 is the only, the hardest one in the final exam. So don't worry about that. Don't worry about that. And when you hear, oh, this is the hardest chapter, the many of you, the maybe, that must be so hard. I need to spend a lot of time. Not necessarily. If it is easy chapter, the problem, I need to make the problem as complicated possible. If it is the hardest chapter, I need to make the problem as easy as possible. So, they can be balanced, isn't it? Anyway, I don't know why I said that, but let's solve these three problems together. The first one is a household refrigerator with a COP of 1.2 removes heat from the refrigerated space at a rate of 60 kilojoule per minute. We want to determine the electric power consumed by the refrigerator and the rate of heat transfer to the kitchen air. Sounds pretty easy. So let's do that. How do we, analyze, the household refrigerator? Here is the equation, COP of refrigerator. So I'm going to use that equation. COP of refrigerator can be determined by Q dot F over W dot net, but that's not it. We have one more equation, Q dot F over Q dot H minus Q dot F. So in this equation, we know COP, that is 1.2. Then, what is the rate of heat transfer from the refrigerated space? That is Q dot F. So this one is 60 kilojoule per minute. Then 1.2 is 60 divided by W dot. Can you determine W dot? Yes, you can. What is W dot? 50 kilojoule per minute. Then let's look at the right-hand side of this equation. Okay, so this one is a 60, this one is a 60. So what is Q dot H? Super easy, isn't it? 110 kilojoule per minute. So that's how you solve this problem. Any question? That's very easy. Can I what? 1.2 is 60 divided by 110 minus 60. Or W is QH minus QL. 50 is this one minus 60. So 110, right? Any question about the first problem? Not much, right? So let's go to the second problem. A refrigerator is used to cool water from 23 degrees Celsius down to 5 degrees Celsius in a continuous manner. So that's a steady state system. The heat rejected in the condenser is 570 kilojoule per minute, and the power consumption is 2.65 kilowatt. We want to determine the rate at which water is cooled in liter per minute. Oh, that's ugly. And the COP of the refrigerator. Okay, let's do that. So we have a refrigerator R. This one has how many thermal energy reservoirs? Always two. High temperature thermal energy reservoir, TH. Low temperature thermal energy reservoir, TR. The rate of the direction of heat transfer is from low temperature to high temperature for the amount of Q dot H, for the amount of Q dot L. And to make that happen, we need to provide W dot net. So that is a refrigeration cycle. Now there is a cooling water in the evaporator. So this water is being cooled from 23 degrees Celsius down to 5 degrees Celsius. So there's water is flowing. Water at the inlet number 1, the temperature T1 was 23 degrees Celsius. At the exit number 2, the temperature was 5 degrees Celsius because this water, rejects heat to the refrigeration cycle. So now we want to determine the mass flow rate of this water. Once you determine the mass flow rate, and then you can convert this mass flow rate to determine the rate in liter per minute later. Okay, let's do that. The power consumption is 2.65 kilowatt. The heat rejected in the condenser. So heat is being rejected from this refrigeration cycle. So is it QL or QH? It's going to be QH because it is the heat rejected from the refrigerator. So Q dot H is going to be 570. Do you like 570? No, because it's a kilojoule per minute. 570 kilojoule per minute. I don't like minute. So let's, the multiply by 1 minute is 60 seconds. Then we can cross minute. Then we have kilojoule per second, which is kilowatt. So what is the value? I don't have it. Do I have it? 9.5. 9.5 kilowatt. Then what is Q dot L? According to the energy balance equation, W dot net is going to be Q dot H minus Q dot L. This is the energy balance equation for this refrigerant system. And Q dot L is going to be, I don't know, Q dot H is going to be 9.5. W dot net is 2.65. Now we can determine Q dot L, which is 6.85 kilowatt. Then now, can you determine the COP? Yes. How do you determine COP? COP of refrigerator can be determined by desired output Q dot L over required input W dot net. Q dot L is going to be 6.85. W dot net is going to be 2.65. So what is the COP? The COP is going to be 2.58, which is greater than the previous problem, only 1.2. So this one is better than 1.2, right? Now, we want to determine the flow rate of this water. Then how can you determine the flow rate of this water? You need to come up with a governing equation for this water. What kind of governing equation? The energy balance equation for this water system. Water is flowing this way, and there's a heat loss. So do you know how to determine the energy balance equation for this water? Yes, there are only two energy balance equations that you studied. One is for a closed system. The other one is for an open system. Is it an open system or a closed system? It's an water is flowing this way. Open system. So the inlet is 23, exit is 5. So it's an open system. What is the general energy balance equation for an open system? Q dot in plus W dot in plus inlet is number 1, M dot at the inlet. This inlet has what? Enthalpy, kinetic energy, and potential energy. And Q dot out plus W dot out plus M dot at the exit, number 2. This water at the exit has specific enthalpy, H2. Specific kinetic energy, V2 square over 2 plus specific potential energy, gravity times elevation, Z2. Then, are we going to use this energy balance equation as is? No, we are not a scientist. I'm not offending any scientist, but I'm just saying that we can simplify this equation. How can we simplify this equation? We can neglect kinetic energy change between these two. Can we? No, there's only one inlet, one exit, unless there's a significant, the diameter change between the pipes at the inlet or exit. We can assume that the velocity is going to be similar. We can assume that density is going to be similar. We can assume that, the density times velocity times cross-section area is also similar. So there's not much difference in velocity. There's not much difference between kinetic energy. There's not much kinetic energy change between the inlet and the exit because the velocity may remain constant unless inlet is this small, exit is this big, which is very unusual. So you can neglect kinetic energy change. What about, the potential energy? This one is the entrance to the mountain Everest. This is on top of the mountain Everest. Not such a case. So you can neglect potential energy change. Any energy transfer by work? Oh, there's a work. But this work is for the refrigeration system. There's no work for this water system. Is there heat transfer? Yes, water is losing heat. How do we know it's losing heat or absorbing heat? Look at the direction of heat transfer, going outside. So heat is being lost from this water. So this Q dot L, is it Q in or Q out? Q out, yes. So this one is Q dot L. And how many inlets, how many exits? Just one. So M dot at the inlet, M dot number 1, is the same as M dot number 2. Should we say M dot 1, M dot 2? No, just M dot. So let's remove the subscript. Then we have m dot h1, m dot h2. Can we move this one to the left hand side? Yes. Then what is the energy balance equation? M dot h1 minus h2 is q dot L. This is the energy balance equation. Much easier than this one. Then we know Q dot L, 6.85 kilowatt. Can we determine H1 minus H2? It depends. Is there phase change? Phase change between 23 degrees Celsius water and 5 degrees Celsius water? No. So can we assume that it's a pure liquid? Yes. How do you determine the change in specific enthalpy when you have a pure liquid? Specific heat, right? No? Just for your information, when you have pure system, H2 minus H1 is CpT2 minus T1, U2 minus U1 is CvT2 minus T1. We have H1 minus H2, it's going to be what? Cp T1 minus T2. M dot is Q dot L. Then what is T1? 23. What is T2? 5. What is Cp? 4.18. So we have everything. So this one is 4.18 kilojoule per kilogram degree Celsius. We have T1, 23 degrees Celsius. We have T2, 5 degrees Celsius. We have M dot in front. I don't know what it is. We have a Q dot L, 6.85 kilowatt. So can you determine M dot? Yes. Then what is M dot? M dot is, do I have it? 0.09104 kilogram per second. That's it? Not really. We want to determine the rate of this water in liter per minute. Liter per minute. This one is mass flow rate, kilogram per second. Liter per minute. This is the mass flow rate? No, liter is volume. It's a volume flow rate. So how can you determine volume flow rate from mass flow rate? M dot is density times volume flow rate. That means volume flow rate is mass flow rate divided by density. So volume flow rate is mass flow rate divided by density. So what is the mass flow rate? 0.09104 kilogram per second. What is the density? Density is 1 kilogram per liter. 1 kilogram per liter. Then what do we have? Kilogram. 0.09104 liter per second. But we want the unit to be liter per minute. So we have second. So 60 seconds is 1 minute. So multiply by 60 seconds per minute. Then we can cross second. Then the volumetric flow rate is 5.46 liter per minute. So that's how you determine the volumetric flow rate. Any question? No question? Yep, I guess so, because this is too easy, isn't it? So I guess that most of you thought that this is too easy. You're so bored. So I'm sorry about that. So I'm going to make a little more challenging problem. So the last problem looks a little bit complicated. So let's look at that. Here is the last problem. Refrigerant 134 enters the evaporator coils placed at the back of the freezer section. Yeah, you can have it. At 100 kilopascal with a quality of 20% and leaves at 100 kilopascal and minus 26 degrees Celsius. If the compressor consumes 600 watts of power and the COP, again 1.2, we want to determine the mass flow rate and the rate of heat rejection to the kitchen air. Okay, let's do that. So we have a refrigerator again. So many refrigerators. And how many thermal energy reservoirs do we need? We need 3. No, we need 2. TR and T what? H. What is the heat transfer direction from low temperature to high temperature? At the rate of Q dot L and at the rate of Q dot H. And to make that happen, we need to provide power. In this case, TH is the temperature of the kitchen air and TL is the temperature of refrigerated space. Now, we have evaporator coils placed at the back of the freezer section. So what does it do? It is at the back of the freezer section trying to absorb heat from whatever, the inside the freezer. So is it Q dot L or Q dot H? Q dot L, right? So what's inside? Maybe some ice cream, another ice cream. So there's ice cream. 3 scoops, 4 scoops, 5, 7, etc., etc. So the refrigerant is flowing in the refrigeration cycle. So the refrigerant is absorbing heat from this refrigerated space. So Q dot L is the heat transfer into or out of, into the refrigerant. Because the refrigerant is absorbing heat from the freezer section. Then what you need to do is you need to write down the energy balance equation for the refrigerant. What is the energy balance equation? You don't remember? That's okay. To start with the easiest and I mean the most general energy balance equation. It's a steady state open system. Let's say inlet is number 1. This one has enthalpy, kinetic energy, and potential energy. It's going to be Q dot out plus W dot out plus M dot at the exit, enthalpy, and kinetic energy and potential energy. First of all, you can neglect kinetic energy change and potential energy change. And is there any energy transfer by work to the refrigerant inside the freezer? No, it absorbs heat, that's all. So the refrigerant is absorbing heat at the rate of Q dot L. Is it Q dot in or Q dot out? It's absorbing to Q dot in. So this Q dot in is Q dot L to the refrigeration system. And there's no Q dot out. There's only one inlet, one exit for this evaporator. So M dot at the inlet is the same as M dot at the exit. So let me remove these subscripts. So we have the rate of enthalpy at the inlet, the rate of enthalpy at the exit. So the energy balance equation is going to be Q dot L is going to be M dot H1 minus H2. Okay, so we are ready to solve this problem. We have the energy balance equation, however, we have no idea about this Q dot L. So let's determine this Q dot L. By how? We can evaluate this refrigeration system. When you have a refrigeration system, we can calculate COP of the refrigerator. How can we do that? Desired output Q dot L over required input W dot net, or we can also say Q dot L over Q dot H minus Q dot L. So in this case, COP is 1.2. This one is 1.2. The power consumption is 600 watt. So this one is a 600 watt. Then we know W dot net is 600, COP is 1.2. Can you determine W dot L? Yes, 720. So this one is 720 watt. Then, can you determine H1? Let's see, what do we know at the inlet? At the inlet, pressure P1 is, let me write it here. At the inlet, let me write it here. At the inlet, pressure P1 is 100 kilopascal, and the quality X is 20%, 0.2. Oh, we know the quality X is 0.2. That means that it is phase change process number 3, saturated mixture. What about at the exit? At the exit, the temperature is minus 26, pressure is 100. Pressure is P2 is 100 kilopascal, temperature T2 is minus 26 degrees Celsius. So from this, we can find H1. From this, we can find H2. Can we determine M dot? Yes, we can. That's how we're going to solve it. So let's find H1 first. How can we determine H1? It is saturated mixture. If you have a saturated mixture, we can use linear interpolation equation. H1 is HF plus quality X1 Hg minus HF. The quality X is 0.2. We just need to find HF and Hg. How can we find HF and Hg? It's simple. We know the pressure. So HF at 100 kilopascal, Hg at 100 kilopascal. So there is 100 kilopascal, HF is this number, Hg is this number, right? So HF is 16.29, Hg is 231.35. Can we determine H1? Yes. What is H1? 59.30 kilojoule per kilogram. Now, H2, how can we find H2? We cannot find H2 directly because we do not know the phase change process. Isn't it 3 anymore? No, not anymore, because there's a heat transfer. It is observed from the refrigerated space. So it's probably phase change process number 4 and number 5, but let's verify that. How can we do that? We can use property diagram. What kind of property diagram? We can make TH or TH, and I want to make TH diagram at this pressure at 100 kilopascal. pH diagram looks like this. And we need to know T set HF, HG. Where can we find T set HF, HG from this pressure? At 100 kilopascal, T set is minus 26.43 degrees Celsius. Oh wait, we know the temperature at the axis. It is minus 26. So where is minus 26? It's greater than minus 26.43, slightly greater than this value. So somewhere here, we have phase change process number 5, superheat vapor. If you know you have a superheat vapor, you can go to superheat vapor table. Here, superheat vapor table, this one, at 100 kilopascal, we are looking at minus 26. So the first temperature is saturation temperature, this one, minus 26.43. The second temperature is minus 20. So minus 26 is between these two numbers. So H value is going to be between these two numbers. You need to do a linear interpolation to determine H at minus 26. Okay, if you do, H2 is going to be 231.7. And H2 is going to be from table A 12, 13, I don't know, 231.7 kilojoule per kilogram, directly from a table. Then this number goes up here to 31.7. This number goes here, 59.3. Oh, I made a mistake. It is H2 minus H1. So the other way. This one goes here. This one goes here. Can you determine m dot? Yes, m dot is 0.004176 kilogram per second. So that is the mass flow rate of the refrigerant. Any question? Yeah, why not? What is the rate of heat rejection to the kitchen air? That is Q dot H. Since this one is 720, 720, 720, we can find Q dot H, 1320 watt. That is the heat rejection. Any question about this problem? Huh? This one, blue. 0.004176 kilogram per second. Any question about this problem? So we studied how to evaluate the performances of heat engine, refrigeration cycle, and heat pump cycle. Then let's talk about, that was the first half of this chapter 5. The second half is pretty easy. But to understand the second half, we need to know some characteristics about the second law of thermodynamics. The first one is Clausius' statement. It is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from a lower temperature body to a higher temperature body. Sounds very complicated? No, it means that you cannot transfer heat from low temperature to high temperature without any external work. If you don't power on, you cannot cool the low temperature, right? That's what Clausius' statement means, which is the basic of the second law of thermodynamics. It transfers from high temperature to low temperature. The second one, Kelvin-Planck statement, which is very interesting. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. What does it mean? When you have a power plant, there's no cooling system. You just burn fossil fuel and then you can produce electricity without cooling it. Is it possible? Not really, but why? If you can produce electricity, from one thermodynamic reservoir, that means if you burn fossil fuel and create 1 kilowatt of heat, you should create 1 kilowatt of electricity. Otherwise, there's a leftover heat that you need to reject. Is it possible? Not really. Why is that? If you convert every single thermal energy of the fossil fuel to work, that means the temperature of the temperature of the working fluid should be what? 0 Kelvin. Because you are converting 100% of heat into electricity. Then what is the thermal energy left over? Nothing. What is the temperature when there is no thermal energy? 0 Kelvin. So at the exit of the turbine, the temperature should be minus 273 degrees Celsius. Can you do that? No. Even going to that temperature is extremely hard. That's why you need two thermal energy reservoirs. One is high temperature, the other one is low temperature, unless you can convert every single thermal energy into mechanical energy. That can be possible if the Earth is maintained at 0 Kelvin. So, because of this, many perpetual motion that doesn't work is based on, it is developed violating this law. And every perpetual motion, if you look at that, there is only one single, the thermodynamic reservoir. That's the problem. We need to reject waste heat, otherwise the system doesn't work. Now we are going to talk about something interesting. Before we talk about reversible and irreversible processes, let me talk about one thing. Let's assume that that we want to work for a power plant company. I want to work for a power plant that produces electricity for Mount Pleasant and our CMU campus. Sounds interesting, right? Then what do you want to do? When you work for that company, you don't want to just do some maybe you want to improve performance of the power plant. So by improving their design, you can enhance their efficiency. You can decrease the cost of electricity. Sounds amazing, right? So let's talk about that. Then, how can you, improve the efficiency? Let's say there is a power plant that runs at efficiency 40%. Can you improve it? Maybe, right? Then can you achieve 100% efficiency? Let's say that you are the god of engineer. Can you achieve 100% efficiency? Not really, because we need to reject waste heat. As long as there is a waste heat, you cannot achieve 100%. Then the next question is, then what is the highest number? What is the highest number? It depends. But isn't it better to know, what is the theoretical possible maximum efficiency? Then, when you achieve the maximum efficiency, let's say that the maximum efficiency of this particular power plant is going to be, let's say, 50%. Then, if it is running 40%, then if you work a lot, if you spend your entire life, maybe you can, raise this value from 40 to 42, 43, 44. That's a great contribution in the power plant industry, right? Then how can we know, the 50% is the maximum? And when do we say it is the maximum? This power plant may have, the lots of turbines and lots of heat exchangers, boilers and pipes and pumps and cooling system, etc., etc., etc. Every single device, there is energy loss. Because of this energy loss, you cannot achieve 100%, right? Then, what about, if you can, achieve the ideal performance of each device in this power plant cycle? That's when you can achieve 50%. Then when is that ideal condition? When a process is reversible. What does it mean, reversible? A process that can be reversed. That means, let's assume that this is hot coffee. Of course, this is cold coffee. But let's assume that this is hot coffee. Initially 100 degrees Celsius, boiling. I just leave this coffee on this desk. About 2 hours later, the coffee is going to be room temperature. So it's a cooling process, right? Which is not reversible process. Reversible process means once it cools down and magically absorbs heat from the surrounding and it boils again. That's a reversible process. The best way, the easiest way to explain reversible process is to use this pendulum. What is pendulum? So let's say that you have a pendulum like this. It is moving back and forth. And we know when it is, going this way and back and forth, we know initially it has the maximum potential energy, and this potential energy is converted to kinetic energy, and we have the maximum velocity right here. That means the maximum kinetic energy, and this kinetic energy is going to be converted to potential energy, and there's no kinetic energy. Now this potential energy is converted to kinetic energy, and this is the maximum kinetic energy, and this kinetic energy is going to be converted back to potential energy, and this is when we have maximum potential energy. So that's how it is going back and forth. So there's a continuous energy conversion between kinetic energy and potential energy, right? So do you think that it's going to be, the continuously, the moving back and forth after 2 hours later, 3 hours later? We know that it's going to, slow down and eventually stop in the middle. We know that for sure. And why is that? While it is moving back and forth, due to the friction between the surface and the air, the friction is going to create heat. That means that some of the kinetic energy is going to be converted to heat. So, the kinetic energy is going down, and potential energy is going down, and eventually, when every potential energy and kinetic energy is converted to heat, it's going to stop in the middle, right? This is irreversible process. Once it stops, you cannot move back and forth without any external force, right? Right? Then what about if I place this pendulum inside a vacuum chamber? Now it's a vacuum chamber. Can this one move back and forth continuously? Yes, no. Assuming that there is no friction. Yeah, it can move back and forth. Then, when this process is reversed, and that reversed again, this is reversible process. In this reversible process, there is no energy loss. So when we assume that every process in this power plant is reversible, then we say it has the maximum efficiency. So the way to calculate the maximum efficiency or maximum performance, we assume that the process is reversible. Okay? Then let's talk about one more example. Okay, it's not vacuum chamber anymore. There's a ceiling is broken, so now we have air. Then, when this pendulum is moving back and forth, and eventually it will stop somewhere, maybe after 5 minutes or 10 minutes, right? What about if you fill this tank with water? It's going to, move back and forth for 5 minutes? Not anymore. After once or twice round, it's going to stop. So when you have water in it, the friction is even more significant. So you lose much more energy. That means if it is vacuum, it's going to be completely reversible. But it is air and it is water, there is a difference even though they are the same irreversible process. Some irreversible processes are close to a reversible process. Some irreversible process is far away from reversible process. So depends on irreversibility of each process. One process can be close to the ideal process. The other process may be far away from the ideal process. So some, the power plant can operate at 40%. Some power plant can operate only at 30% or 20%, depends on irreversibility in the power plant. That's why, when you drive, the Prius or any hybrid car, for the same 1 gallon, you can drive from here to maybe Saginaw. But if you drive a dump truck, you can only, the 10% of, the hybrid can drive, because one has more irreversibility than the others. Make sense? So when we design an engineering system, the minimizing the irreversibility is the way to improve the efficiency. Okay? Let's think about this way. Let's assume that you're working for a computer, the company. So a company that produces a laptop. So you want to design a new laptop that has, one of the best CPUs. I don't know. Let's we prefer, the AMD or, the Intel. Intel is easier to count because they are numbering system, right? i3, i7, i9, and let's assume that this is i2000. Extremely fast CPU. And you install, the NVIDIA GPU. and RAM is, the 2000 terabytes RAM, and the hard disk drive is only 1 megabyte. Is it going to run? No. Why is that? Hard disk drive is too poor. So the irreversibility of that device is so poor. So you can catch that, okay, this one has a lot of irreversibility. So let's improve this one. So if you replace the hard disk drive, then you can dramatically improve the performance. But what about if you replace? I think the CPU is the problem. So let's replace this I2000 with I2001. Is it going to make a significant change? Not much, because there's a less irreversibility. Identifying, which one has the highest irreversibility is the, that determines, the how well you can design a product. Okay, so in that sense, let's go back here. So whenever we design an engineering system, we prefer, to design a system, even though it is not reversible, we want to make this irreversible process close to a reversible process. That's how we improve the efficiency. Okay? Then, when we assume that we have everything is reversible, that cycle is called Carnot cycle. So when we have a heat engine, the ideal heat engine is called Carnot heat engine. When we have a refrigeration cycle, the ideal refrigeration cycle is going to be Carnot refrigerator. When we have a heat pump cycle, the ideal heat pump cycle is called Carnot heat pump cycle. When we say Carnot cycle, means that we assume that every, the process in the cycle is completely reversible. So that is the ideal system that has the highest performance. So that's how we calculate the highest efficiency, theoretical maximum efficiency. So today we are going to learn how to evaluate the performance of Carnot cycle, which is very simple. Then, before we actually study how to determine the performance of this Carnot cycle, let's learn about one example why it is necessary. Okay. So let's it is always best to understand a principle by comparing two different examples. So let's assume that you want to work for a power plant company. One more time. There are two power plants here. So there's one power plant is producing electricity for Mount Pleasant. So there's a power plant company number one, power plant company number one, which is in Mount Pleasant. And there's another power plant company which is in Midland, Michigan. Power plant number two, Midland. Then, how do we evaluate the performance of this power plant? Power plant is a heat engine, so you can calculate the efficiency. How do we calculate the efficiency? Desired output, W dot net, over required input, W dot H. So when you calculate the efficiency, it was 30%. It's pretty high. What about the efficiency of the power plant in Midland? Oh, it was only 10%. So let's assume that you have a dream. I want to improve the performance of a power plant by by modifying the present design, trying to minimize the irreversibilities, trying to minimize the friction, trying to minimize the heat loss. So we want to improve the efficiency. Which one is easier to improve? Maybe one can say 30%. So you think that it is easier to increase 30% to 40% rather than 10% to 20%. Only thinking about improving efficiency point of view. Which one is easier? Huh? What? Yeah, Midland. That's reasonable because that the numbers seem to be too low. So there must be something very stupid thing is going on. I can just go there. Oh, that's stupid. Let's fix it. Then we can dramatically increase 10% to 20%. Sounds reasonable. You can make that decision when you only study the first half of this chapter 5. Now, if you study Carnot heat engine, you can calculate what is the maximum efficiency possible in theory. So let's do that. If you assume that every process in the power plant number 1 is reversible, the maximum efficiency turns out 50%. So there's a room for 20% improvement. And when you calculate it, the maximum possible efficiency for power plant number 2, it is only 11%. Now, if you studied, the entire chapter 5, now you can do this analysis. If you chose this power plant number 2 to improve this 10% to 11%, how long it's going to take? Is it even possible to achieve this ideal system? Not really. So if you, jump onto this power plant, spend 50 years from now on, you may not be able to achieve 11% unless you are the god of engineer. What about here? There's 20% room. So maybe there are a lot of, funny businesses going on. You can fix it, and then you can achieve, 33%, 35% easily. If you can do this analysis, you can make that decision. If you do not able to calculate, if you're not able to calculate the theoretical maximum, then you can simply choose this one. Could be wrong decision, right? So today, what we are going to do is that we are going to learn how to determine the theoretical maximum efficiency. That is called Carnot efficiency. And by the way, is it difficult? Not at all. This is the easiest one in the thermodynamics history. Okay, so let's talk about that. How can we determine Carnot efficiency? So we studied, the 3 cycles. The first one is heat engine. The second one is refrigerator. The third one is heat pump. How do we evaluate their performances? We use the efficiency. How do we determine this efficiency? Desired output over required input. By the way, W.net is the same as Q.H minus Q.L. So we can say this one is the same as Q.H minus Q.L over Q.H, which is the same as 1 minus Q.L over Q.H. So that's how we determine the efficiency. This is the actual efficiency of a heat engine. What about refrigerator? How do you evaluate the performance? We use a COP. COP of refrigerator can be determined by desired output, Q.L, over required input, W.net. You can also say COP of refrigerator can be determined by Q.L over this one, Q.H minus Q.L. What about heat pump? You can calculate COP of heat pump. What is the desired output? The heat transfer into the indoor divided by W.net, which is Q.H minus Q.L. Then, if we say we have a Carnot system, in other words, the cycle is completely reversible. So it has all reversible processes inside. If you assume that, the efficiency of this ideal heat engine, which is reversible, can be determined by, it's very simple. You just need to replace this Q with temperature T. 1 minus TL over TH. COP of refrigerator, which is reversible. TL over TH minus TL. COP of heat pump, which is reversible. TH over TH minus TL. So that's how you determine the maximum performances. So this one slide has everything that you need to know in terms of this chapter. Then let's solve a problem together. Oh, wait. Yeah, it's still there. So let's look at the first problem from a work production perspective. It means that if you have a heat engine, which is more valuable? Thermal energy reservoirs at 675 and 325, thermal energy reservoirs at 625 and 275. What does it mean? For this power plant, it is provided at 675 Kelvin to the turbine, and the cooling water is provided at 325. The temperature difference is what? 350 Kelvin, temperature difference. And another, the power plant, whose turbine inlet temperature is only 625, and the cooling water temperature is 275. What is the temperature difference? Again, 350. So the first one would be the power plant built in the southern area, let's say Texas. And the second power plant is the power plant built in the northern area, like Michigan. Because outside, the coolant temperature is less here, and then, the turbine inlet temperature is less, but the temperature difference is the same. As long as the temperature difference is the same, it sounds like they have provided us about the same thermal efficiency. However, if you actually calculate the maximum possible efficiency, the answer is not right. So let's calculate the theoretical maximum efficiency of the first power plant, which is in Texas. How do we calculate that? 1 minus TL over TH. 1 minus TL, 325 Kelvin, divided by TH, 675 Kelvin. We got 0.519, which is about 51.9%. So that is the maximum possible efficiency you can achieve from this power plant. Of course, the actual value will be less than that. What about the power plant B in the northern region? The theoretical maximum efficiency can be determined by 1 minus 275 Kelvin divided by 625 Kelvin. So what is the value? 0.56. It is 56%. So if you have the same design, if you build a power plant with the same design, even though it shares the same component, same turbine, same condenser, it is probably, better to build that in northern area because it has a higher potential. Okay? Any question? I think that's about it today. We are going to continue, the solving a few more problems this Thursday. I think that will be all for chapter 5. And our next second exam is going to be next Thursday. Okay? Yes.